Hi everyone. So, D1 matches, this is going to be really quick. This is a quick video because this is a quick topic. Uh, I've looked at other ones, because I don't normally make the D1 videos and I just think, just dragging this out, man. So let's just go for it. Uh, like Hegarty's one's half an hour long plus a 15-minute tutorial. I reckon we can get this down in, I don't know, in 15 minutes. So, let's do it. So D1 matching, this is like I say, a brief topic, and the idea of it is, it's quite fun actually. The idea of it is, if if you look at this bipartite graph, okay, so this is called a bipartite graph, which means that there are two sections of nodes. As you know, bi means two. Um, And these sections of nodes can represent anything. So ACHJR, let's ignore the example for the moment. This could be jobs, this could be sweets, this could be pots of money, let's say. Okay? And these jobs, sweets, or pots of money can be linked to people. Um, people, other jobs. Uh, I don't know, bank managers, if it's pots of money. Okay, do you see? So you've got two sets of nodes separated from each other, and they will never be able to be linked. So if you've got, the idea is in the matching essentially is if you had 5 jobs, you'd have 5 people who can perform certain jobs. You need to make sure that every single person has a task, or every single task is being allocated to a person. Okay, so in a bipartite graph, you can never have H connected with J or 1 connected with 3. You see? You can only connect between one half and the other half. So a letter with a number, a letter with a number. Do you see? Okay, so definition of a bipartite graph is essentially two sets of nodes that cannot be interconnected within each set. It can only be connected from one set to another. Okay? Now, what is this thing that you're looking at? Well, let's have a look at it. So, figure 3, is we're just going to learn this through example. And like I say, the idea, and it's called the maximum matching algorithm. The idea of this is to allocate all tasks to all people. Now, figure 3, as you can see, so this one here shows the possible allocations of 5 workers: Adam A, Catherine C, Harriet H, Josh J, and Richard R, to 5 tasks: 1, 2, 3, 4, 5. What does this thing on the left mean? Well, this shows that Adam A here, Adam is able to perform task 1 and is able to perform task 3, i.e. has the skills in order to do that. H for Harriet, she can perform tasks 1, 2, and 3. Okay? But remember, our task is to make sure one person is allocated to one task. So if you imagine you're in a workplace, someone couldn't turn up for their shift, and you have to provide cover for them. You have to shift all of your staff around in order to make sure that that thing was covered. And especially if you're in a factory or something like that, working in a factory where certain people know how to do certain jobs, it kind of also shows the advantage of upskilling all of your workforce, doesn't it? Make sure that they can do as many tasks as possible, and that way, if anyone is ill, they can be covered. Okay? Because at the moment, Jay, who's Jay? Josh. Well, he's pretty, I was going to say useless, but not useless, but he can only do task 4. So he's not very flexible, is he? There's not much he can offer outside of doing task 4. Okay, so figure 4 shows an initial matching. So that's what this right-hand side is about, okay? So this is possibles on the left, essentially, and this right, this is our initial. So as it stands, we have 3 people allocated to 3 jobs, and there are 2 jobs and 2 people missing. Okay, so our task is to use the maximum matching algorithm in order to uh, link up A with a task and J with a task as well. All right. Now the matching algorithm, this can only match one pair at a time. Okay, so if there are 2 nodes missing, then you have to perform this twice. 3, then you have to perform it 3 times. Yes, you could do it by inspection by eye, but as I've said, as you build up more nodes, and that's what decision is all about, as you build up more nodes, or if you're putting this into a computer system, then it has to follow an algorithm. And what we would deem as obvious is just completely irrelevant and out of context, really. Okay, so where do we start? And what does the algorithm look like? Clearly, we can start anywhere. Let's start with A. So in the question, they may say start with A, starting with Adam, link up to a task. So we're going to start with A, and we're going to go from here. So what jobs can Adam do? Adam can do job 1 or job 3. So if I give Adam job 1, at the moment, job 1 is allocated to Harriet. Do you see? And therefore, if that's allocated to Harriet, Harriet's job now needs to switch, doesn't it? So how would I actually perform this stuff? Well, personally, I would draw a new set of nodes. So 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. And in your exam, they'll give you this set of nodes because it gets difficult to keep up with it. Okay, so now I'm saying Adam is going to take job 1. But job 1 at the moment is taken by Harriet. So now Harriet's job needs to change. What can Harriet do? Harriet can do 1, what we've said, but we've already allocated that to Adam. But we can also do job 3. And job 2 is one which hasn't been allocated to yet. So therefore, I'm going to allocate Harriet to job 2. So Harriet is now job 2. Do you see? And wow, we have now matched a person to a missing node. Do you see? So this would be interpreted as a breakthrough. So how would I write this? I would write BT here. This is a breakthrough because now we have a missing person to a missing node. What is this thing that I've written down here? Well, this is called an alternating path. So you could write, so an alternating path is what it's called. But we'll just call that A dot P, do you see? So A dot P, and how would I start my algorithm? Well, I would say where it is I'm trying to go. So I've done it informally here, now I'm going to do it formally for you. So I'm going to say alternating path, and I'm going from A, aren't I? And I want to go to a missing node, so 2 or 5 is available. I don't know which one I'm going to go to yet, all right? So I'm going to fill that in a second. So A to that, we start off with A, we went to 1, and let's be clear what these signs mean then. That dash meant A is currently to 1. Or I'm putting A to 1 now, okay? So A is to 1 now, but 1 is equal to Harriet, which means Harriet is now going to go to 2. Do you see? This was our breakthrough, so I'd write B dot T. Our algorithm's finished, and now we need to do what's called changing status. So change status means that now A isn't going to 1, A is 1, isn't it? Do you see? And H is now 2. So in other words, all the what look like equal signs and minus signs switch over. And now we have a new matching, a new initial matching then, because we're saying A is 1. Has C changed? No, C is still 4. H has changed, hasn't it? H is 2. J is still unmatched. And remember, we can't do that yet. We have to do another matching algorithm after this. And R is still 3. Do you see? So there's your new initial matching. If I now want to complete the matching, and if we just repeat that question, by the way, alternating path A, and then we matched up the whole thing to 2. So my alternating path is A2. Do you see? And therefore, to finish this path, or to finish my matching, this forms my new initial matching to fill out the next task. So it always helps to draw the nodes again. So A, B, C, D. Ugh, no, it's not. Okay, so A, C, H, J, K. 1, 2, 3, 4, 5. So at the moment, A is to 1, C is to 4, H is to 2, J is unmatched, and R is to 3. So I want to complete my matching this time, so alternating path. This time I want J to go to something, so I'm not saying J is going to 5, but I'm saying J is the unmatched node and 5 is the unmatched node. And now we're going to go for our alternating path. So our alternating path, let's go for it. So we're starting at J. Again, like I said, it helps if you draw your dots out again so you can see what's happening. So A, C, H, J, R. 1, 2, 3, 4, and 5. So let's go. We're starting at J. Where can J go? We know that J can only go to 4. So J, therefore, is gone to 4. So J is to 4. But 4 was allocated to C. So therefore, C now has to move. You see? Because we're working off this one now, aren't we? So C, what can C do? C can do 3, 4, or 5. And if that's the case, and we know that 5 is missing, then we'll go from C to 5 then, and then it's sorted. So that's our breakthrough. So this is a really easy example. We're going to change our status. So J is now 4, C goes to 5, new matching, J equals 4, C equals 5, and A still is 1, C, as we've already written, was 5, H is still 2, and R is still 3. Done. Let's do another example. Again, you may need to rewind the tape and try this again. So, new matching this time, new situation. Figure 3, you've got 6 different people, 6 different tasks, and then figure 4, we've got our new initial matching. It says part C, starting from this initial matching. Again, pause the video and do it by yourself if you want and compare. Use the maximum matching algorithm, which we already know what it is, to find an improved matching. You should list the alternating path you use and state your improved matching. So let's go for it. So part C, we are going to do our dots because that's helpful. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. We've got C, E. Again, this is all in your answer book in your exam, so don't worry, you won't have to draw these out every time. Okay, cool. So, alternating path, and we want to match up, well, what's missing? J's missing, isn't it? So J to something, don't know what it is yet, because there are 2 different options, we don't know exactly where it's going to go. So let's start with J. So what can J go to? J can go to 4. So J is now to 4, but 4 was allocated to E. So now E is going to have to change. If E changes, well, where can E go? E can go to 4, as we know, but it can also go to 2. So E is now going to go to 2. So this was E, and now this is 2. 2 was, so we use the equal sign, 2 was allocated to C, yeah? But now C is going to have to be reconfigured, and C, as we know, can go to 2, but can also go to 3. And there we go, we've got a breakthrough, because now C is at 3, and 3 was one of our unmatched nodes. So breakthrough, B dot T. Remember what I said in decision maths? Mark really harshly, and therefore you have to follow all these steps. And J went to 3. Okay, so now you guessed it, change status. So J is now 4, E is now 2, and C is now 3. So new matching. J is 4, E is 2, C is 3. What else we got? G is 1, that hasn't changed. C, E, G, H. H hasn't changed, that's still 6. And S is still unmatched. Yeah, cool. And then Emily has, so we've done that bit, done. And state your improved matching, we've done that. Okay, that's our improved matching here. Emily has task 5 added to her possible allocations. So, starting from the improved matching found in part C, use the maximum matching algorithm to find a complete matching. You should list the alternative path you use and state your improved matching. Also, Harriet has task 3 added to her possible allocations. That's interesting. Normally there'll be a question saying, well, can we complete the matching? And if you look at it, if you investigate it, no, we can't. We can't complete the matching without those tasks being added. And I wonder if you can spot why. So I'll let you have a look at that. Harriet, so Emily has task 5 added, so Emily is here, so that's now added. And Harriet has task 3 added, so there we go. Let's try again then. So part D, let's finish this off. Part D, alternating path. Our initial matching is now this one, isn't it? So I already started drawing it up here, so I could just use that matching, but to make it a bit easier to look at, let's go C, E, G, H, J, and S. 1, 2, 3, 4, 5, and 6. So this can be our new initial matching. So that's C to 3, J to 4, E to 2, C to 3 is done, G to 1, H to 6, and S we don't know. Okay, so alternating path, S has got to go to 5, isn't it? They're the two ones which are missing. And we'll start from S then. So S is currently mapped to, where's S mapped to? Nothing. So S can be mapped to 6, which we can see. So 6, but 6 is currently matched to H, which we know from here. So H, therefore, needs to be adjusted. H we know goes for 6, but now it also goes to 3. So H goes to 3 now. But 3 was allocated to C, you see? And remember, we're stopping when we get 5 matched. So C can go to 2 and 3. So now C is going to have to go to 2. But 2, if we follow this back, is currently matched to E. So now we need to go back to E, and E can be matched to 2, 4, or 5. So let's match it to 5 because that's where or how we're trying to finish. That's what we're trying to accomplish. So we've done it. Breakthrough, change in status. S is now 6, H is now 3, C is now 2, and E is now 5. So our new matching, or complete matching, because it is a complete matching now, S is 6, H is 3, C is 2, E is 5. So that's 4 of them. And we've still got G, and that hadn't changed. That's 1. And what else? J. J is 4. That hadn't changed. So we're finished. So that's the maximum matching algorithm. That's the whole topic. I just threw this off the cuff. So hopefully you've got this and you understand. Just remember it can only find one at a time. Okay? And I think that's it. That's